Sorry, I pressed the wrong thing. Here we go. There we go. Okay. So that's what happens here. Okay. So I showed you how to do it on the Desmos calculator. If you want to use factorials, that's fine. I'm just saying you don't have to. So, you know, if you were to put this down and then put the answer, that's really what I'm looking for. Okay. Now, here we want the probability of selecting exactly one jack. Okay? We want the probability of getting exactly one jack. So, how many ways can you do that? Well, remember there are 4 jacks altogether in the deck. Okay? There are 4 of them in the deck. Right? So how many ways can we choose a jack? Well, there's only 4 ways because there's 4 jacks in the deck. We only want one of them. But since we only want one, the other 4 cards cannot be jacks, right? They have to be 4 cards from the remaining 48 possibilities. So because of that, to get the other 4 cards, right, there's only 48 possibilities because they can't be any of the 4 jacks. We're choosing 4. Again, it's without regard to order and without replacement. So for the other 4 cards, we have this. So we have C of 48, comma 4. That's for the remaining 4 cards in the 5-card hand. In the poker hand, that's better. Okay, so if there are 4 ways we can get the first card, there are this many ways we can get the next 4 cards. By the counting principle, there are this many ways. The number on top, 4 times C of 48, 4, we can get a 5-card poker hand with only 1 jack. This is how many ways. And again, the sample size, that's the word, the phrase I mean, the size of the sample size, you know, the total number of outcomes altogether is the C of 52.5, as you can see. Okay? Right? Because again, you know, in the same scenario, we want to know how many possible ways you can get a poker hand, which is 5 cards, from 52 cards. We don't care about order and without replacement. So this is our probability. Okay. So that's for 1 jack. And for 2 jacks, it's actually very similar. Namely, for 2 jacks, right, we have, well, again, there's 4 jacks in the deck, right? Again, there's 1 for each suit, right? So there's 4 jacks, excuse me, in the deck. So how many ways can we get 2 of them? Again, we don't care about order, and it's without replacement. So we have C of 4, comma 2. That's how many ways we can get 2 out of the 4 jacks. So that's how many ways we can get the 2 jacks. But again, we have a 5-card poker hand, right? So because of that, we have to handle the other 3 cards. But again, the other 3 cards can't be, you know, you can't have jacks in them. They can only be from the 48 remaining possible cards. So how many ways can you get those 3? That's what this is. Okay? So altogether, again, by the counting principle, you just multiply. In other words, the total number of ways we can get a poker hand of 5 cards, 2 of them are jacks, and the remaining 3 cards are not jacks. Well, by the counting principle, it's this product on top here. Okay. And again, right, this is probability. We're in the same scenario where these are the total number of possible outcomes. That is, the total number of outcomes equals how many ways we can get a poker hand of 5 cards from the deck of 52 cards. That's what the denominator is. Okay? So this is what we get. So the probability is this big quotient, which turns out to be that. Okay, good. Now the last one, I know it seems kind of out of place. It's actually not that bad. You want the probability of getting exactly 2 aces and 3 kings. Okay? You have 2 aces and exactly 3 kings. Okay? Okay. Well, we know that we're choosing 5 cards again, right? Again, the scenario is, of all the possible 5-card poker hands you can get, we want the probability of getting a 5-card poker hand that has exactly 2 aces and 3 kings. Okay, well, for the 2 aces, we know there are 4 aces in the deck. So how many ways could we get the 2 aces? This is how, C of 4, 2. Okay. Now for the 3 kings, well, there are 4 kings in the deck, right? How many ways could we get the kings? Well, it's really the same idea, except instead of a 2, you have a 3 here. So C of 4, 3. Okay, well, so by the counting principle then, the total number of possible 5-card poker hands with 2 aces and 3 kings would be C of 4, 2 times C of 4, 3. And from that, okay, the probability then would be C of 4, 2 times C of 4, 3. That product is actually 24 divided by C of 52, 5, which is this. So that's what the probability there would be. Yeah, good. All right. Are there any questions on that? All right. Here's another one I want to do. So this was a little bit of extra probability, so to say. If you have 2 events, A and B, okay? If you have 2 events, A and B, right? The probability of A and B occurring, okay? So you have 2 events, you want to know how likely is it both events will occur, okay? It's the probability of A times the probability of B given that A has occurred. Remember, this is what we call conditional probability. This is the probability of A. This is the probability of B given A. That's what this is. And this brings us into the notion of 2 events being independent. Basically, 2 events are considered independent if the probability of one event occurring does not depend, is the same regardless whether the other event occurs or not. So if you have 2 events, A and B, let's say, right? The probability of A given that B has occurred is the same as the probability of A given that the complement of B has occurred. Remember, this bar, if I remember correctly, is the notation we use for the complement of an event. The complement occurs if the event does not occur. So the probability of A occurring, okay, it's the same if B occurs or if B does not occur. That's what we're saying. And again, you know, I just rewrote this. A and B are arbitrary, so I really didn't have to write both equations, but I just felt like I should. Okay? But this is really in words what we're saying. The probability of one event occurring is the same whether or not the other event occurs. So, and I just threw in this example as well with a bag of marbles.